Problem sheet 2, question 4. A printing shop owns 4 printers. Each printer breaks down at a rate beta. Once broken down, it is sent for repair. The rate at which printers get repaired is alpha. Letting I be the state that there are I printers in operation, draw the Markov chain for the system and find the steady state probabilities for general alpha and beta, and for when alpha is equal to beta. Okay, first of all, is this a discrete time or a continuous time Markov chain? Because the question is ambiguous, but we know that there are rates of repair rather than probability of being repaired at a certain time. Therefore, this must be a continuous time Markov chain. What are our states? Well, there are 4 printers, and at any time, some of those can be out of service. So our states would be 0 printers in service, 1 printer in service, 2 printers in service, 3 in service, and 4 in service. When all printers are in operation, state 4, the rate at which a printer breaks down goes from 4 to 3 is beta per printer, but there are 4 printers. When there are 3 printers in operation, the rate at which they break down again is beta, and there are 3 printers, so 3 beta. When there are 2 printers in operation, the rate at which each of them break down is beta, and there are 2 printers in operation. And when there is 1 printer in operation, the rate at which it breaks down is just beta. Now, similarly, for the rate at which they get repaired, we can see this as a symmetric process. When there are 0 printers in operation, there are 4 being repaired. Each is getting repaired at a rate of alpha, but there are 4 printers getting repaired. When there is 1 printer in operation, there are 3 printers being repaired, each getting repaired with a rate alpha. There are 2 printers in operation, there are 2 printers getting repaired with a rate alpha. There are 3 printers in operation, there's 1 printer getting repaired at rate alpha. So this is us drawing the Markov chain for the system. What would the transition rate matrix look like for this? Well, we already have an ordering of the states, 0, 1, 2, 3, 4. So our transition rate matrix, denoted by Q, would be the rate at which you go from 0 to 1 is 4 alpha. The rate at which you go from 0 to any other state is 0. And remember that the diagonal for a transition rate matrix will be the negative of the sum of the rows. So in the diagonal of this matrix, we will put minus 4 alpha on this row. For state 1, the rate at which you go from state 1 to state 0 is beta. From 1 to state 2 is 3 alpha, 0 elsewhere. And you need the negative of the sum of the row on the diagonals. This would be minus beta plus 3 alpha. Similarly, for state 2, state 3, and state 4, which would be our transition rate matrix. To find the steady state probabilities of a continuous time Markov chain, we want to solve pi q is equal to 0, while remembering that the sum of a probability vector is equal to 1. Generally, that means we want to find the probabilities such that the rate going into a state is equal to the rate out of a state. So for state 0, the rate out of the state would be 4 alpha pi naught, and the rate into that state would be beta pi 1. For state 1, the rate out of the state is going to be beta plus 3 alpha pi 1, and the rate out of the state is going to be 4 alpha pi naught plus 2 beta pi 2. For state 2, the rate out of the state will be 2 beta plus 2 alpha pi 2. And the rate into the state is going to be 3 alpha pi 1 plus 3 beta pi 3. For state 3, the rate out of the state is 3 beta plus alpha pi 3. And that's going to be equal to the rate into the state, 2 alpha pi 2 plus 4 beta pi 4. Finally, for state 4, the rate out of the state is 4 beta pi 4. That's going to be equal to the rate into the state, which is alpha pi 3. We also want to remember that pi 0 plus pi 1 plus pi 2 plus pi 3 plus pi 4 is equal to 1. In order to solve this, we need to do some algebraic manipulation. So let's label these equations so that we can refer back to them. This should be label 1, 2, 3, 4, 5, and 6. The tactic to solve this will be putting everything in terms of one of the variables. Let's choose pi 0. If we consider equation 1, we have pi 0 and pi 1, so we can put pi 1 in terms of pi 0 by dividing through by beta. Pi 1 is equal to 4 alpha over beta pi 0. For pi 2, we can consider equation 2. This is an equation of three unknowns, pi 0, pi 1 and pi 2, but we have pi 1 in terms of pi 0. So we can write this as beta plus 3 alpha, 4 alpha over beta pi 0. That is equal to 4 alpha pi 0 plus 2 beta pi 2. Expanding this out, we would get 4 alpha pi 0 plus 3 times 4 is 12 alpha squared over beta pi 0 minus 4 alpha pi 0 is equal to 2 beta pi 2. Simplifying, we will get 12 alpha squared over beta pi 0 is equal to 2 beta pi 2, which is going to give us pi 2 is equal to 6 alpha squared over beta squared. To put pi 3 in terms of pi 0, we will consider equation 3. 2 beta plus 2 alpha pi 2 is equal to 3 alpha pi 1 plus 3 beta pi 3. Pi 2 and pi 1 we both have in terms of pi 0, so we can make that substitution. 2 beta plus 2 alpha times 6 alpha squared over beta squared pi 0. That is equal to 3 times alpha times 4 alpha over beta pi 0 plus 3 beta pi 3. Simplifying this, we can get 12 alpha cubed over beta squared pi 0 is equal to 3 beta pi 3, and so pi 3 is equal to 4 alpha cubed over beta cubed pi 0. Finally, for beta 4, let us consider equation 4. 4 beta pi 4 is equal to alpha pi 3. We now have pi 3 in terms of pi 0. So we can write 4 beta pi 4 is equal to 4 alpha to the power of 4 over beta cubed pi naught. And therefore pi 4 is equal to alpha to the 4 over beta to the 4 pi naught. To find the value of each of these, we will then consider equation 6, which is the equation that says the sum of the probability vector must be equal to 1. So that was pi naught plus pi 1 plus pi 2 plus pi 3 plus pi 4 is equal to 1. We can make our substitutions. So everything was in terms of pi naught. So pi naught plus pi 1 was equal to 4 alpha over beta. Pi naught. Pi 2 was equal to 6 alpha squared over beta squared. Pi naught. Pi 3 was equal to 4 alpha cubed over beta cubed. Pi naught. Pi 4 was equal to alpha to the power of 4 over beta to the power of 4 pi naught, which is equal to 1. We can factor out a pi naught. And so pi naught is equal to 1 over this large sum. And all the other probabilities are in terms of this pi naught. Finally, the question asked, what is the steady state vector when alpha is equal to beta? If alpha is equal to beta, then I know my pi naught is going to be equal to 1 over, and now I have a lot of fractions that cancel out. So it's going to be 1 plus 4 plus 6 plus 4 plus 1 over 16. I know that pi 1 is going to be 4 alpha over beta pi naught, which is going to be 4 lots of 1 over 16, which is equal to 4/16 or a quarter. Pi 2 is going to be 6 alpha squared beta squared pi naught, which is going to be 6 lots of 1 over 16, which is 6/16 or 3/8. Pi 3 is going to be 4 alpha cubed over beta cubed pi naught, which is going to be 4 lots of 1 over 16, 4 over 16, which is 1 over 4. And finally, pi 4 is going to be alpha to the 4 over beta to the 4 pi naught, which is just going to be 1 lot of pi naught, which is 1 over 16. And so my steady state vector pi is going to be 1 over 16, 1 over 4, 3 over 8, 1 over 4, 1 over 16.